Hi everyone! In this lesson, we'll explore the importance of data analysis in viticulture. In this module, we'll look at the role of data in viticulture and the key steps in the decision-making process driven by data. We will also see the use of the decision support systems and the role of the algorithm in the machine learning. The module concludes with a panoramic view of the pros and the challenge of the use of AI, and we'll discuss why ethical considerations matter when using AI in agriculture. Today's vineyards are awash in information, from detailed soil sensor readings and drone scans to satellite imagery and weather station reports. The pivotal challenge is no longer gathering this vast amount of data, but rather what to do with it. Raw data without insightful analysis remains merely a collection of numbers. The true competitive edge emerges when this data is transformed into actionable knowledge, enabling growers to make strategic, evidence-based decisions, fine-tune irrigation, fertilization, and disease control, accurately forecast yields to minimize waste, and proactively identify issues before they impact production. In essence, for contemporary viticulture, data transcends simple figures. It's the foundation for optimizing vineyard operations, elevating grape quality, and fostering long-term sustainability. Modern farming thrives on quantifiable information for objective decision-making. The real success lies not in the volume of data acquired, but in our ability to interpret it effectively to boost vineyard productivity and profitability. Only through meaningful interpretation does data unlock its true value. The image illustrates the evolution of agriculture through distinct historical stages conceptualized as agriculture 0.0 inches to agriculture 4.0. Agriculture 0.0, preceding the Industrial Revolution, represents farming before mechanization and the Green Revolution. This is followed by agriculture 1.0, or industrial agriculture, characterized by the introduction of tractors, combine harvesters, and general machinery, along with the outsourcing of inputs. The next stage, agriculture 2.0, advanced mechanization, precision agriculture, highlights the integration of onboard technology like guidance and electronic control, VRT, isobus, remote sensing, satellites, aerial UAVs, and sensor networks. Agriculture 3.0, or digital agriculture, emphasizes the use of GIS, digital notebooks, decision support systems, and fleet management. Finally, Agriculture 4.0 represents a permanent network of information exchange, defined by smart digital ecosystems, systems of systems, the smart integration of bits and bytes, and ubiquitous cyberspace, aiming for 30 MB per s in all rural areas by 2020. In modern viticulture, making informed decisions is crucial for optimizing vineyard management, and precision viticulture plays a transformative role in this process. The decision-making process is a dynamic cycle that starts with vineyard monitoring and data collection, where advanced technologies record the vineyard's condition and a variety of factors affecting the vineyard, like soil conditions and weather patterns. These technologies provide real-time data to ensure precise monitoring of the vineyard. Once the data is collected, it's stored in a secure system where it can be accessed and analyzed. Data storage is crucial to ensure that historical data is available for comparison and trend analysis. The data is then processed through advanced transforming technologies that clean, organize, and analyze it, often through software that uses algorithms to extract meaningful insights. By identifying patterns and predicting future vineyard needs, this step transforms raw data into actionable information. Decision-making follows, where vineyard managers make informed choices based on the analyzed data. After decisions are made, it's time for the operational implementation, where strategies are put into action on the ground, supported by guidance technologies which assist in the accurate execution of decisions. Finally, after the decisions are implemented, the cycle returns to data collection, where the results are monitored and new data is gathered, feeding back into the loop. Actions are monitored, and the data is analyzed again, refining future decisions and improving vineyard management continuously. This iterative process, driven by data, is key to achieving sustainable and high-performing vineyards. Several tools enable data collection in vineyards, including proximal and remote sensing technologies that utilize different measurement methods. In modern viticulture, databases serve as the essential backbone for collecting, storing, and meticulously organizing vast amounts of critical information. These digital repositories centralize a wide array of data points crucial for vineyard management. This comprehensive information includes detailed soil properties such as pH, moisture levels, and composition, extensive weather data encompassing temperature, rainfall, and wind patterns, vital plant health indicators like leaf color and disease occurrence, as well as crucial yield statistics and harvest history. Furthermore, they track pesticide and fertilizer usage and integrate complex geographic information systems (GIS) data. By consolidating all this diverse information, these databases empower growers to easily access both historical and real-time data, enabling them to gain a profound understanding of vineyard conditions and emerging trends for more informed decision-making. Decision support systems help farmers to face the increasing complexity of decision-making for crop protection and vineyard management. The figure shows the scheme for a decision support system for plant disease management. The process begins with sensing and ends with actions, as we have seen before. The DSS provides information and guidance to the user, but the user makes the decisions. In modern agriculture, a decision support system, DSS, serves as a crucial tool, leveraging data stored in databases to simulate potential outcomes, forecast emerging trends, and ultimately recommend optimal courses of action for growers. Specifically in viticulture, the application of a DSS can significantly enhance vineyard management. This includes enabling precise irrigation scheduling by integrating real-time weather forecasts and soil moisture levels. It also powers pest and disease prediction models, utilizing both historical and current environmental data to anticipate outbreaks. A DSS can help optimize harvest time by meticulously tracking grape ripening indicators, guide fertilization strategies based on identified nutrient deficiencies, and inform canopy management decisions by analyzing growth data and sunlight exposure. These data-driven decisions collectively lead to improved yield and enhanced grape quality, while simultaneously contributing to reduced waste and a minimized environmental impact. This figure illustrates a comprehensive scheme for the development of a decision support system, DSS, specifically designed for the integrated management of vineyards. This DSS aims to assist farmers in navigating the increasing complexity of decision-making concerning crop protection. As demonstrated by the EU project MODEM_IVM, Monitoring and Decision-Making in Integrated Vineyard Management, the scheme details the various activities, tools, data flows, and subjects that are interconnected and involved in building such a system. The overall goal is to streamline and optimize the decision-making process for effective vineyard management. A decision support system needs to integrate key components to ensure practical usability. It includes automatic interpretation procedures that transform processed data into actionable agronomic advice and a graphical interface, which allows users to interact with the DSS, access insights, and tailor recommendations to their specific needs. Interoperability is also crucial, enabling the DSS to integrate multiple monitoring and prediction systems, connecting with various data sources, for example, sensors, weather models, and farm management platforms, for more accurate and efficient decision-making. Utilizing databases within decision support systems, DSS, offers significant advantages for modern viticulture, transforming traditional guesswork into precise data-driven strategies. This integration leads to increased precision as decisions are no longer based on assumptions but on concrete data, thereby significantly reducing human error. Consequently, it fosters improved efficiency in resource management, ensuring that valuable inputs such as water, labor, and chemicals are used far more effectively and with minimal waste. Furthermore, by enabling continuous monitoring of environmental factors, these systems greatly enhance the sustainability of vineyard practices, promoting eco-friendly approaches. The ability to take preventative actions, informed by accurate and timely data, also contributes to substantial cost reduction over time by mitigating potential problems before they escalate. Finally, the availability of comprehensive historical data empowers vineyard managers with crucial insights for long-term planning, supporting strategic decisions that can optimize operations and yields across multiple seasons. Despite the clear advantages, implementing robust databases within decision support systems, DSS for viticulture, comes with its own set of significant challenges. Firstly, there's the hurdle of high initial costs. Establishing such a system requires a substantial investment, not only in advanced sensors to collect the data, but also in specialized software and the underlying database infrastructure itself. This can be a considerable financial burden for many vineyards. Secondly, the technology is only as good as the people using it, which highlights the need for extensive training requirements. Workers need to be properly trained not just to accurately input data, but also to correctly interpret the information and insights that the DSS provides. This demands time and resources for skill development. Another complexity arises from data integration. Modern vineyards utilize data from a myriad of sources, including drones, on-ground weather stations, and various other field sensors. Merging and harmonizing all this disparate data into a single cohesive database can be technically complex and time-consuming. Furthermore, as with any data-intensive system, privacy and data ownership issues can emerge, particularly when vineyards opt to use third-party software or cloud-based solutions. Understanding who owns the collected data and how it's protected becomes a critical concern. Finally, practical limitations related to infrastructure and network coverage often pose a significant challenge, especially in remote rural vineyard areas. Consistent and reliable internet access is crucial for real-time data flow and effective operation of cloud-based DSS components, and its absence can hinder full implementation. As precision agriculture continues its rapid expansion, the role of databases and decision support systems, DSS, is set to become even more vital in viticulture. These foundational tools will be indispensable for managing the increasingly complex data streams associated with highly targeted farming practices. Looking ahead, significant innovations in machine learning and artificial intelligence, AI, are expected to profoundly enhance the predictive power of these systems. This technological leap will enable a much deeper understanding of vineyard dynamics and environmental interactions. Ultimately, this will render viticulture far more intelligent and responsive, allowing growers to effectively adapt to and mitigate the growing challenges posed by climate change. As a key driver of digital transformation, AI future applications are expected to bring significant changes. However, AI is already widely implemented in vineyards, wineries, and distribution processes. AI is transforming vineyard management by providing insights into key factors such as yield and grape characteristics. Machine intelligence, combined with sensor data and imagery, helps wine growers optimize crop care, adjusting treatments to improve yield, determine the best harvest time, and in this way ensure grape quality. In wineries, AI processes sensor data to optimize production. AI can predict wine quality by analyzing the composition of fermentation products, tracking maturation in barrels, and streamlining operations, ultimately saving time and costs. Also, wine marketers use AI to reach the end customer. AI is reshaping wine marketing by, for example, analyzing consumer preferences. An interesting application at the marketing level is virtual reality, which enhances wine tourism, allowing consumers to experience vineyards and wineries from home through immersive tastings. Additionally, the so-called AI-powered virtual sommeliers, by personalizing wine recommendations, are opening new market opportunities, attracting both investors and customers. Machine learning, a key branch of artificial intelligence, empowers computers to learn from vast amounts of data, thereby enhancing their performance without requiring explicit programming for every individual task. At its core, a machine learning system analyzes large data sets to identify recurring patterns. It then leverages this acquired information to autonomously make predictions or informed decisions, continuously improving its capabilities over time. Simple example, a machine learning algorithm can learn to recognize ripe grapes by analyzing thousands of labeled images classified as ripe or not ripe. In machine learning, an algorithm is a set of rules or steps that a computer follows to learn patterns from data and make predictions or decisions based on it. You can think of it like a recipe. It tells the machine how to process input data, find relationships, and improve over time. An algorithm doesn't do the learning itself. It defines how the learning happens. Depending on the task, classification, prediction, clustering, etc., different algorithms are used. In the realm of machine learning, various algorithms are employed to enable systems to learn from data and make predictions or decisions. Let's look at two fundamental examples. Linear regression. This algorithm is designed to predict a numeric continuous value based on given input data. It essentially finds the best fit line or hyperplane that describes the relationship between the input variables and the target output. For instance, in viticulture, linear regression could be used to predict the price of a bottle of wine by analyzing contributing factors such as its alcohol content, acidity, and sugar level. The algorithm learns how these numerical features influence the final price, allowing for an estimation of new, unobserved wines. Decision tree. A decision tree algorithm makes decisions by progressively splitting data into branches based on a series of rules, much like a flowchart. Each internal node represents a test on an attribute. Each branch represents the outcome of the test, and each leaf node represents a class label or a decision. A practical application in viticulture would be to classify whether a grape is ripe or not. The algorithm would analyze features like the grape's color, size, and sugar content, making a decision at each step until it reaches a conclusion about its ripeness level. Machine learning has three key components: algorithms, features, and data. Algorithms are the methods used to solve a problem. The algorithm works to optimize accuracy, performance, and the size of the model. It's through this process that the system learns and adapts. Features refer to the parameters or variables that are used to train the model. In the context of a data set, these are usually the column names when the data is in table form. For example, in viticulture, features could include parameters like grape variety, soil moisture, temperature. Data plays a central role. For instance, when the goal is to detect diseases in vines, the system needs images of the diseases to learn from. The more diverse the dataset, the better. There are two primary ways to gather this data: manually or automatically. In viticulture, machine learning is used to improve wine quality, optimize farming practices, and reduce cost. Here are some practical applications. 1. Crop monitoring. Sensors and drones collect data on temperature, soil moisture, sunlight exposure, and leaf imagery. Machine learning analyzes this data to detect plant stress, diseases, or nutrient deficiencies, often before they are visible to the human eye. 2. Disease prediction. Predictive algorithms can forecast the appearance of diseases such as downy mildew or powdery mildew by analyzing weather data, treatment history, and the current state of the vines. This allows for more targeted and sustainable interventions. 3. Harvest optimization. Machine learning can accurately predict the optimal time for grape harvesting based on parameters such as phenolic and sugar ripeness and evolving climate conditions. 4. Grape quality classification. Using visual and chemical analysis, algorithms can classify grapes based on quality, helping wineries select the best clusters for different types of wine. Artificial intelligence is rapidly transforming the agricultural landscape, paving the way for farming practices that are remarkably more efficient, precise, and deeply data-driven. From advanced predictive crop modeling to sophisticated automated pest detection systems, AI empowers farmers to make significantly smarter decisions, thereby minimizing waste and boosting overall productivity. Nevertheless, this swift integration of AI technologies into agriculture also brings to the forefront important ethical concerns. These issues demand careful consideration and proactive addressing to ensure that such powerful innovation serves all stakeholders fairly and contributes to genuinely sustainable agricultural systems. AI in agriculture brings clear advantages. Machine learning models can predict weather patterns, soil needs, and crop yields with high accuracy. Drones and smart sensors can monitor plant health in real time, reducing the need for excessive chemical inputs. These tools can support sustainable agriculture by optimizing resource use and minimizing environmental harm. Moreover, AI can assist in tackling food insecurity. With better forecasting and automation, AI helps maximize yields even in challenging conditions, which is especially valuable in regions affected by climate change or labor shortages. Despite the considerable advantages offered by AI in agriculture, its widespread adoption also brings forth critical ethical issues that demand careful consideration. These concerns primarily revolve around several key areas. Firstly, questions of data ownership and privacy are paramount. as vast amounts of sensitive agricultural data are collected and processed. Secondly, there is a risk of bias and ensuring fair access to these technologies, preventing a widening gap between those who can afford and implement AI solutions and those who cannot. Thirdly, the complexity of AI systems raises challenges regarding transparency and accountability. It can be difficult to understand how AI makes decisions and who is ultimately responsible when things go wrong. Lastly, a significant concern is labor displacement, as increasing automation might reduce the need for manual labor, potentially impacting agricultural employment and rural communities. To ensure AI is used ethically in agriculture, several steps are necessary. Develop clear guidelines for data governance that protect farmers' rights. Promote open and inclusive data sets to reduce algorithmic bias. Ensure transparency in AI systems so users understand how decisions are made. Support education and training for farmers to use AI tools effectively and responsibly. Encourage collaboration between governments, tech companies, and farming communities. Ethical AI is not just about avoiding harm. It's about ensuring justice, inclusivity, and long-term sustainability in agricultural innovation. This concludes our lesson. Thank you, and see you in the next lesson.